Okay, I'm going to describe this project, and this is what it looks like. We are going to have, this is site 1, and then we're going to have, site 2. Let's look at the differences. Site 1 has a layer of silt and a layer of clay, sandwiched between gravel, sand, gravel. Now notice, this layer is double drained and that layer is double drained. So we have double drainage for both the silt and clay layer for site 1. For site 2, we just have a single clay layer and it is underlain by rock. So we have a single clay, we have a clay layer and it is single drainage. So that is the fundamental difference between these two sites. In addition, the sand is layer 1, the clay is layer 2, and these are the soil properties of layer 1. These are the soil properties of layer 2. Again, layer 1, layer 2. We have all those soil properties. We may not use all of them, but for the time being you do. And then we do have some strength information here as well. Undrained strength information. Same thing with site 1. I have all the soil properties for all the different layers. These are the different layers here, and we have more properties there, and we have some undrained strength information right there. Like I say, we may not use all the properties given. So what we're going to do at these sites is, this is my t equals 0 minus condition right there. So I just have my soil. I have an elevation of 0 at the top, and then it goes down to 54 feet where I hit bedrock at negative 54 feet. Then we are going to place 12 feet of fill at our site, and that fill could be sand or gravel, so we have different conditions there. And so this is the t equals 0 plus condition where we put on the sand or gravel fill to act as a surcharge. So we leave that fill, and that fill can be on there for 5 years or 20 years, so it's a different case. And I'll explain all the cases. And then, let's say we leave it on for 5 years. Well, it's going to be there for more than 5 years, but we put it on for 5 years, and then we put on, at t equals 5 plus, we put on a structure. And that structure could be this one with no basement, this one with a basement. The weight of the structure is the same, 4 million pounds for both of those. So, like I say, we could put the structure on at 5 years, or we could put the structure on at 20 years. So, two different cases. And the basement that we are going to use is 10-foot basement. So, the weight of the structure is 4 million pounds. When we put on the basement, it's a 10-foot basement. You can see because the elevation is 12 there, and at the bottom of the basement it's 2, so it's a 10-foot basement. 10 feet deep. If I said 12, that's a mistake. It's 10 feet. So we have a building with no basement. We have a building with a 10-foot basement. For site 2, it's the same thing. So we put on sand or gravel, 12 feet. It'll be there for 5 years or 20 years before we put on either of these two structures. So we put on the structure at either 5 years or 20 years. What we're going to do is we want to figure out our goal will be to determine the center settlement of the structure. So that is our goal. We're just going to compute the center settlement. And put it this way, at the center settlement at 25 years. That's our goal, is figure out what is the center settlement at 25 years. For both of these, center settlement 25 years. So, okay, so in a nutshell, we have 16 cases here, and they're labeled 1 through 4, 5 through 8, 9 through 12, 13 through 16. So you need to evaluate 16 different cases, and these are what they are. So we have site. Whoops. We have site 1 here. So all this pertains to site 1. And then we have site 2 here. All this pertains to site 2. It's basically the same thing. So, so it's site 1. We have the situation where we put on 12 feet of gravel at 116 pounds per cubic foot. And then we put the structure on at 5 years with no basement and a basement, 10-foot basement. We put the structure on at 20 years, no basement, 10-foot basement. Same thing with when we look at the sand. I put the structure on at 5 years, no basement, 10-foot basement. I put the structure on at 20 years, no basement, 10-foot basement. So I have 8 different cases to analyze for site 1. And then I have the same 8 cases for site 2. So in other words, I have 12 feet of gravel. 12 feet of gravel, 116 pounds per cubic foot at site 2. And 5 years, then we put on the structure, no basement, 20 years, then put on the structure, no basement. And then I can do the sand, 5 years, then the structure, no basement, 10-foot basement. 20 years, then the structure, no basement, 10-foot basement. So those are the 16 cases I'm going to analyze. I'm going to show you the details of how to analyze these. And again, I want my settlement at 25 years. So my goal is to get the settlement at 25 years of the center of the structure. So, okay, how do we analyze this? So I'm going to do one of the cases. Well, I'm going to do 2 of the cases for you. So even though I've listed 16 cases, you only have to do 14 because I've already done 2 of them for you. So I'm going to show you how to do case 1. Case 1 is going to be, so I'm going to give you a blank spreadsheet that looks like this. You can create your own spreadsheet. You can use this. It's up to you. But the details of case 1 are what? Well, we're looking at site 1 for case 1. We're putting on 12 feet of gravel at 116 pounds per cubic foot. So in other words, what I'm showing here is this. Okay? So I'm putting that information onto my spreadsheet so it's handy. And for case 1, it's 5 years before I put on this. Then I put on the structure. I don't have a basement. The basement depth is 0. So the structure. Let's start at the beginning here. Since there's no basement, the Q, the surface load, ends up being 4 million pounds. That's the weight of the structure, and the structure is 50 by 50, has a square footprint 50 by 50, so the area is 50 squared. So that gives me 1,600, and I should put on the units there. The units are in pounds per square foot. So, but all of the stresses here are in pounds per square foot, and all the lengths are in feet. So we can add those. I don't show all the units, but units, the stress, is in PSF, and the length is feet. So those are the units we're using. So, all right, so what do we do to handle this situation? Well, if you look back at our notes, since we have things changing with time, we have to set up two different time schedules. So in other words, we have a T1. Oops. We have a T1 and a T2. So now you'll notice, and the way that we're going to set it up is we're going to follow the fill with one time scale, and then we'll follow the structure with a different time scale. So, in other words, T1 follows the fill, and I put on the fill at T equals 0 plus, and it stays there for 25 years. But at 5 years is when I put on my structure. So for this case, for case 1, I want my time schedule, I want to have 0, 5, and 25. 0, 5, and 25. So that is case 1. Why 0, 5, and 25? Because it's 5 years that I put on the structure. Now, this little top spreadsheet is for the silt layer at site 1. The bottom little spreadsheet is for the clay layer at site 1. Because if you remember what we have at site 1, so here's my site 1, I have a silt and I have a clay. And, nothing happens to it. So I have silt and clay, and so I have to analyze both layers. For site 2, I only have the clay, so I only have to worry about one of them. So, okay. All right, so I set up my two time scales, and the way that it works is, so that my time scale for the building is what? Well, at 5 years, at 5 minus, that's 0 minus for my building. At 5 plus, that's 0 plus for my building. So I have, 0 minus here, 0 plus here, and then at 25 years, well, that's 20 years for my structure's been up there for 20 years. So that is my time scale. So T1 is for the fill, T2 is for the structure. Same thing here, T1 for the fill, T2 for the structure, and these times are the same as these times, so it's pretty easy. Those are the same, those are the same. So those are my two time scales. Then what do I need to do? Well, then I need to put together my my T1 and my T2. Now, capital T's. If you remember, the equation for T, capital T, T is equal to C sub V T over HDR squared. So I need to use my value of C sub V for my layer, and I need to use my HDR for my layer. So we've computed those, but maybe I'll just list them right here. So we have for the clay and the silt, what are the HDRs? The HDRs are, remember, it's double drainage. For that silt, it's half. Well, the total thickness of the silt is 22 feet. So my HDR is half of that, which is 11. So I have my HDR equals 11 feet, and I look at my C sub V, is, for the silt, is 4.84. So, and that is in square feet per year. For the clay, well, that thickness is 8 feet, and that means my HDR is 4 feet, and my C sub V is 0.82 square feet per year. So that is how I'm going to get my equation for my T. And like I say, you've done some of this already, but so for the silt, what do we have? I'm gonna write it down right here. So so for the silt, that is C sub V is 4.84 T over HDR squared, which is 11 squared. And for the clay, it's going to be C sub V, which is 0.82 times T over 4 squared. So I'm able to get my equation for T up here works out to be 0.04 T, 0.04 times small t, and then this is 0.0513 times small t. So I'm going to take, so this, I take the 5, I put it in there, and I get 0.2. And they're both at 5, so I get both 0.2. And then at 25, I take the 25 and I put it in there, and I get 1. So that's how I get the capital T's for that. For capital T1. For capital T2, it's 20, so I take the 20, I put it in there. Or, easier, put it in there, and I get 0.8. I do the same thing down here. So I take the 5 and I put it in here, I get 0.257. I take the 25, I also put it in there, I get 1.28. That gives me capital T1, and then for capital T2, I put the 20 there, and I get 1.03. So that's how I get all my T's. Now, like I've said many times, the whole key to these problems is getting the U-excess. If you get the U-excess, the hard part is pretty much done. So let's look at, like I say, the T1, small t1, capital T1, they refer to the fill. And so UXS1 also refers to the fill. And what is the excess pore pressure at T equals 0 plus? Well, T equals 0 plus is what? I'm putting on 12 feet of gravel at 116. So at T equals 0 plus, it's 12 times 16. So I get 1392. So that gives me the T equals 0 plus UXS. And then I look at 5 years, I look at my capital T1, which is 0.2. So so I'm looking at a capital T1 of 0.2. Well, what do I do with that? Well, then I go into my chart. Now remember, it's double drainage, so I use the whole thing. And my point of interest is at the middle of the silt layer. So we had And now I've forgotten. I think it was point two. What was it? Yeah, T1 is 0.2, so I go back to that. I'm looking for T1 of 0.2, or T of 0.2, so there's T of 0.2. I'm at the middle. My point of interest is at the middle, because remember, this is the top of the silt. This is the bottom of the silt. And so I look in the middle for the middle of the silt, and that's going to give me my value right here, and I read that down here. So that's 0.5, 0.6, 0.7, 0.8. So it's, looks like 0.77 or something like that is what I get for my factor there. And I put that into, and I got 0.77. Yeah, so there's the 0.77. What do I multiply it by? 1392. And I get my 1072 right there. These two then are the same because no time has gone by, so the excess pore pressure hasn't dissipated. And then now I use my value of T1 being 1. So I go back to the same plot, but now I'm at T being 1. I'm again at the middle here, so I'm going to read that off. And that's pretty close to being 0.1 here. So that factor is about 0.1. What did I get? Okay, I used it 0.12, so close enough. And so I get 0.12 again times the 1392. We always go back to always go back to that 0 plus situation. So it's 1392, and that gives me 167. So that gives me my UXS1. For the UXS2, well, let me do this one down here. So down here again, I have the 1392. That's the same. Why? Because it's 12 feet of gravel. It's 116 pounds per cubic foot. So that's what we're gonna get the same, because it's a fill. It covers a large area. It doesn't matter how deep we are. So we still have the 1392. So now I have my 5 years. Well, I have a different equation for T, capital T. So I have a different capital T there. And so I go into the, now I go at 0.257. So 0.257, I don't know, something along these lines. And so again, I'm looking here. I come down here. It looks like about 0.68 or something like that. And again, this is approximate. So what did I come up with? Well, I guess I didn't show it, but it's about 0.68 times 1392. Let's see. 0.68 times 1392. 946. And I guess maybe I got something a little different, but let's see. Oh, 0.65. Okay, so I got 0.65. Close enough. It's hard to read it. These are approximate, so so in this particular case, maybe I'll write it down here, just so that we have it and you. 0.65 times 1392 is 905. So, and then as we go deeper here, now we're at 1.28. Let's take a look at what we have there. That might be a little trickier, but So 1.28, well, now what are we at? Well, there's 1.2. 1.28, well, I'm just going to estimate it. Something like that. It's getting down close to 0. So, but now, I'm in here, maybe 0.05. Remember, this is 0.1. So we're looking at about 0.05 for that point. And let's see what we got here. Okay, I used 0.03. Close enough. It's approximate. So again, it's 0.03 times 1392, and looks like I wrote 1382 there. So let me change that. That should be 1392, and okay, so we got our UXS ones. Now I want to get the UXS2. Well, where does the UXS2 come from? The UXS2 comes from the structure. So we're going to have this structure here at 5 years. So that's at 5 plus. And so at 5 plus, I'm going to have a UXS generated. I don't have, and that 5 plus is what? That 5 plus is 0 plus in our new time scale. That 5 plus is the 0 plus. So that gives me my UXS2. So, my 0 minus, remember our 0 minus here always has a UXS of 0. So 0 minus has a UXS of 0. So I guess I should show that as being 0 here. Oops. So, okay, so then the question becomes, how do we get the UXS at time equals 0 plus for my structure? Well, that's straightforward in a sense. We have to use, and I show this little thing here, that's a little pressure bulb. So there's the pressure bulb to give you a clue that we have to use the pressure bulb. Well, to use the pressure bulb, what do I need? I need the Z and I need the B to get the Z over B. So what is the Z? If you remember, the Z is the distance from the bottom of the foundation to the point of interest. So here I'm showing it as 19 plus 12. Well, why is it 19 plus 12? It's because if we look at site 1, remember, I'm doing it without the basement. I'm looking at the middle of the silt. Well, the middle of the silt is 19. So that middle of the silt is 19. And then I have this 12 here, 12 for the fill. So the total distance is 19 plus 12. So in other words, there's the center of my layer. And that distance then is 31. So that is my Z. Z is equal to 31 feet. So there's my Z, and my building width is 50 feet, so that's my B. So I'm going to use Z is 31, B is 50. That means Z over B is 0.62. So my Z over B is 0.62. What do I do with that? Well, I go into this diagram and I go down. Well, 0.62 is about right in here. Well, that puts me between the 0.5 and 0.6 contour. So, it could be 0.58 or something like that, approximately. Again, it's approximate. So I get, so what do I get? Yeah, I had 0.58 times the 1600. Where did the 1600 come from? Well, the weight of my structure is 4 million pounds. it's a square 50 by 50, so 4 million divided by 50 squared is 1600 psf. So it's 0.58 from the pressure bulb times 1600. That 1600 comes in here. The pressure bulb gives us that. So it's 0.58 times 1600 gives me 928. Now what happens? Now time goes by. That's my t equals 0 plus situation. But at 20 years, now what happens? The pore pressure, excess pore pressure dissipates. Now I have to use my other chart, and that's supposed to mean the pore pressure chart. So I use my T2, which is 0.8, and I come into the T2 of 0.8. So I come back in here, again in the middle. I'm looking for 0.8. There's my 0.8 contour, so I'm looking for the value of that point. I come down here, and it's going to be 0.16 or something like that. So that's about 0.16 that I would read over. Something like that, approximate. So 0.16. Then I come back in here, and I have the, I use 0.17. 0.17 times the 928. Where does the 928 come from? The 928 comes from, because that's the t equals 0 plus number, so it's 0.17 times 928. Now, now what we do for down here, for the clay layer, so remember the top spreadsheet's for the silt, the bottom's for the clay. Well, now my z is different, correct? Because I'm talking about the distance to the middle of the clay layer to the foundation. And that's going to be 42 plus 12, which is 54. So in other words, we are looking at 54. Where does that 54 come from? I'm in the middle of the clay right here. There's my, and you can just look at the numbers. That's 54 feet. How did I get it? Well, that's 42, and that is 12. 42 plus 12 is 54. So that's where I get my z. Again, my b is 50. So my z over b now is going to be the 54 divided by the 50, 1.08. So I take my 1.08, I go into my pressure bulb, I go down 1.08, it's about right there. I read off the contour, it's pretty close to 0.3. And what did I use here? I used 0.3. So 1600 times 0.3, and there's my 1600, that comes down there, and the 0.3 comes from the pressure bulb, and that gives me the 480. Then what do I do? Again, I use my T2, which is 1.03, to get the next one, to get the factor there. So I go into the T2 using this 1.03. Well, where is that going to be? It's going to be in here someplace. Slightly less than 0.1, it looks like, because I come across there. Again, it's double drainage. So slightly less than 0.1. What did I use? I used, well, I guess I used slightly more than 0.11. It's pretty close to 0.1. 0.11. Okay, so like I say, it's approximate. And it's 0.11 times the 480. So comes out to be 53. So, okay, there's our two UXs. Like that's the most important thing. U water table, well, it's 11 feet below the water table, my point of interest, so I get 686. You can figure that one out, that depth below the water table. And so now what do I do to get my U's? Well, I add all these numbers up, and that gives me my U. So I can add, let's take this one, it's easy enough. 905 plus 480 plus 2121 gives me 3506. So you can all add up those numbers to get your U's. Okay, then the next part of it that can be a little bit confusing then is the sigma V's. They're not confusing, sigma V is easy, but you have to pay attention to the right picture. Okay, so notice, to get the sigma V's, I've got to look at my times. To get my sigma V's, I look at the picture with my times. So I've labeled the pictures. So the first picture is t equals 0 minus. So what do? I look at the t equals 0 minus picture, and I get the sigma V at this point. I get the sigma V at this point from the t equals 0 minus picture. I'm not going to go through that. You can all do that at this point. So that gives me the sigma V here and sigma V there. Well, now I want to get the t equals 0 plus to 5, to t equals 0 plus to 5 minus. Well, I look at the t equals 0 plus to 5 minus picture. Which one is that? There it is. So I use this picture now to get my sigma V at these 2 points. You can all do that, so I'm not going to go through that one. And then for the other one, of course, I now use the last picture to get 5 plus to 25 is this picture. Now this picture has the structure on it. So what do I have to do? Well, I'll show you how we do it. And but again, I have, and the way I'm doing it is the pressure bulbs, right? So I have my pressure bulbs that look like that, and that's the principle of it. Now we're going to do a little bit of a trick along the way, but okay, so I got to look at the right picture. So the way that so I've looked at the pictures, and I've gotten these pretty straightforward. Okay, so I've got those. You can all do those because there's no structure there. Now, the easiest way to do this, so I get this number, sigma V, and I already have U. So this number here is 3299 minus the 758. That gives me the 1541. Now, this little trick makes things a little bit easier, is that I have this 1541. Well, what do I know? No time has passed from 5 minus to 5 plus. That means the effective stress has to remain the same. So if I have 1541 here, that means I have 1541 there. So I'm showing this arrow here, so just go right down to that. And then once I've got this and I've got that. We've already computed those. So what do I know? I know that then if I add 1541 plus 2686, that gives me the sigma V of 4227. So I end up with this number simply by adding 1541 and 2686. And then what do I note? Well, if I look at the picture, 5 plus and 25 is the same, so these numbers need to be the same. So I simply put the 4227 here. Now I've got the 4227. I have the U already of 1011, and I take 4227 minus 1011. That gives me 3216. So I now have all of these values. I'm not going to go through it. It's the same process here. Okay, and I do the same trick. So I get to here, and I go down to here, and then I go to here, and then I go to there, and then I go to there. So you can get all of those effective stresses. So we now have all of these numbers, and now my goal is to figure out the settlement of the structure. Well, we don't put the structure there until here, okay? In other words, before I put the structure down, my effective stress in the ground is 2824. That's my T equals 0 minus there, and 1541, that's my T equals 0 minus there. So the way we've always done our settlement is we go from T equals 0 minus to T equals 10 years, 15 years, 20 years, or whatever. So in this case, it's 20 years. So I want to get my settlement at T equals 20 years. And so I'm going to use that as my sigma prime I, and that is my sigma prime I. So I'm going to have, so in my next table here, I'm just going to show you, there's my 1541. So in other words, this goes over here. That's my sigma v prime I, because that's my T equals 0 minus situation. And then I've got my 2824, my T equals 0 minus situation. That's going to be my sigma prime I here. And, okay, my sigma prime F is going to be what? Well, there's my sigma prime F, my 3216 and my 4114, because I'm looking at my answer. I want my answer at 25 years. So there's my sigma prime F. And so the 3216 goes right there. Sigma prime F. 4114 goes right there. That's my sigma prime F. So I've got my sigma prime I and I've got my sigma prime F. Now the little tricky part, in a way, is the sigma prime P. Now, how do we get our sigma prime P? Well, I have to think it out. You have to remember sigma prime P equals maximum sigma prime ever felt by the point. Okay? So that's the definition. Now, I have to look at it and figure out what is the maximum, my point of interest, right? My point of interest I'm talking about. So what is the maximum it's ever felt? I have to compute that. Well, let's look at what is our OCR. So, when we started out, we had an OCR. Let's look at the silt. The silt has an OCR NC. What does that mean? NC means that, if you remember this, normally consolidated, that means the OCR is 1.0. If the OCR is 1.0, that means that that sigma prime P and sigma prime I are the same. So in other words, when I say sigma prime I, here I am in the ground. This is my situation for which I get this. Okay? Or I should draw it this way. This is my situation. That's the situation that gave me that. This situation gave me this. So if I need to figure out what is the maximum stress here that the soil has ever felt. Well, the maximum stress that it's ever felt, I have to go back to my calculations back here. So in other words, let's look at the silt. It's a little more obvious. I have my in situ T equals 0 minus stresses there. And what do? Well, I have to get my original sigma prime P. The OCR was given as 1.05 times the 2237. So in the ground, before we did anything, before we came to the site and did anything, the greatest stress that clay had ever felt is 2453. Now, here we had the OCR of 1, so 1 times 1221 is 1221. So the greatest stress that this had ever felt before we did anything at the site was 1221. So we get 1221 for that one. That's the sigma prime P. But if you look, what has happened for our building? we went up to 1541 and 2824. So what has happened is our sigma, the greatest stress ever before we did anything was 1221 and 2453. But in the process of putting on the fill, we've raised the stress to 1541. So I have to figure out which is bigger. Which of those two is bigger? I'm looking for the greatest. Well, the greatest is 1541. So I compare those two and take the greatest. I compare these two, I take the greatest. So my sigma prime p is bigger now. So I now have my 1541 here is my sigma prime p, 2824. So when I draw my diagram, my 1541 is here, right on the inflection point, and the 2824 is there. So that's how I draw my my diagram. So I have now my sigma v prime I have my sigma prime p, I have my sigma v prime f, and so my diagram begins here and ends here. So there's my, this begins here, it ends here. And so, draw it like this. And so when I do my my epsilon v, it's simply the, just use the second half of the equation. The C epsilon v is C epsilon C is 0.27 for that soil. C epsilon C for that one is 0.2425. And so I take my sigma v prime f over sigma v prime I, sigma v prime f over sigma v prime I. I get my epsilon v's, and then I note the h's. For the silt is 22 feet thick, the clay is 8 feet thick. And I take this times that, and that gives me the delta H there. And I take this times that, and that gives me the delta H there. And I add those two numbers together, I get 2.45 feet. That is the number that I want to work with right there. That is the settlement of the structure. The middle of the structure goes down 2.45 feet under this situation. Okay. I'll do another one in the next video.